So it turns out that Ahmdahl's law doesn't quite apply in the same way to our situation. And the key is the fact that we're not just talking about time for a specific problem, we're talking about time as a function of the size of the problem. Okay. We have a problem where m and n and k are all the same. Then the time that we spend in matrix multiply is 2n cubed times some constant that captures at what rate we compute, plus, and we never did this analysis, but if you analyzed it, you would end up with an overhead term that is something like a constant times n squared times beta, where beta captures something about the bandwidth to memory, and the constant probably has some of the block sizes in it. Okay, so this is really the cost function, or the function that tells us the time it takes to do a problem where each of the matrices is n by n. And maybe we should just kind of dot out Ahmdahl's law, because it doesn't quite apply, or not in the same way. Now, we worked pretty hard on parallelizing the computational part. We've got a bunch of cores. Once the data actually ends up in the registers, we are pretty good at parallelizing that. So it is the case that t, if we use the time, if we use t threads, is roughly 2n cubed gamma over t. And what if we were just completely inept at doing anything about the part that shuffles data between the memories? Okay. What if we didn't make any progress on that at all? So that now becomes the part that we didn't parallelize, and the part that should scare us because of Ahmdahl's law. Okay, well, let's look at speedup. Speedup then is defined as a function of the number of threads and the problem size to be equal to the sequential time, 2n cubed gamma plus cn squared beta, divided by the time spent when you use t threads. So that's 2n cubed gamma over t plus cn squared beta. Okay? And we really are interested in efficiency, and the efficiency is defined to be the speed up divided by t, and notice that that means just multiplying the denominator by t, so that means that this goes away, and we end up with a t for the number of threads being used right there. Okay. If we then manipulate this, and we say, okay, well, we can think of this as this part divided by that plus this part divided by that, we get this. Okay? And now on the left, what we can do is we can say, oh, we can divide this into the denominator, and we get 1 divided by 1 plus t times cn squared beta divided by 2n cubed gamma plus 1 divided by, we can divide this into both sides, and we get 2n cubed gamma divided by cn squared beta plus t. Okay? And then we can cancel the n cubed against the n squared, and we get an n on the bottom, and this here disappears. And then over here we can leave an n up the top and take away the n squared on the bottom. Now notice that once you fix the number of threads, all of this here is just a constant. So it's really a constant divided by n. And over here, all of this here is just a constant, as is t. If you now say, oh, wait a minute, what we've noticed in all of our experiments is that we plot n along the x-axis and we increase n as we go to the right, we can then ask ourselves the question, well, what happens to our efficiency as n gets large? And what you notice is that this here starts going to 0, so this term here becomes 1, and this term right here becomes very large, overwhelming the t, and as a matter of fact adding t to it just makes it larger, and therefore this term eventually becomes very small, starts tending to 0. So what do we conclude? If we can make our problem n large enough, then our efficiency eventually becomes 1, 100%. That's pretty good. Now, of course, there are limits on how big of a problem you can run on a machine. You may run out of memory. So really what this here says is, if we're sloppy about parallelizing the part that comes from moving data around, then if we plot our usual plot where we put gigaflops per thread along the y-axis and the problem size along the x-axis. On a single core you might get performance that looks something like this. And all that this term here does is it slows down how fast your gigaflops per thread approach the performance that you get on a single thread, single core. Okay? Which of course still means that you want to do the best that you can to parallelize also the overhead. Why? Because it allows you to achieve higher performance faster for smaller problems. And that's always a good thing. But Ahmdahl's law doesn't quite apply in the same way in our situation.